Imagine, just for a moment, a control panel for the universe. It's covered in dials and sliders, each labeled with a fundamental constant of nature. One dial, gravity. Another, the electron's mass. A third, the energy of empty space. Reach out your hand and give one dial the tiniest, most infinitesimal nudge. A turn so small you can barely see it move. In that instant, everything you know disappears. Stars, planets, the chair you're sitting on, you. The universe as we know it would be impossible. We wouldn't be here to wonder why. This isn't science fiction. It's a profound and unsettling observation about the cosmos. Scientists have found the laws and constants seem exquisitely balanced, fine-tuned for complex life. It's as if our universe walks a tightrope over an abyss. Let's begin the exploration of the universe that almost wasn't. What do we mean by fine-tuning? Think of it like baking the perfect cosmic cake. The recipe requires very specific amounts of each ingredient. Too much flour, dry and crumbly. Too little sugar, tasteless. The laws of physics are like that recipe. The constants of nature are the precise measurements. Gravity, proton charge, expansion rate, galaxies, stars, us. A recipe of stunning, improbable precision. Let's get more specific. One of these dials, the strong nuclear force, the superglue of the universe. It binds protons. It binds neutrons in the nucleus. If it were a few percent weaker, protons wouldn't stick together. Hydrogen would be the only element. No carbon, no oxygen, no iron. Without heavier elements forged in stars, no rocky planets. No water, no building blocks for life. A thin, uninteresting soup of a single element. Now turn the dial the other way. If the strong force were a bit stronger, protons and neutrons would be unbearably sticky. Nearly all hydrogen would fuse almost instantly into heavier elements. Long-lived hydrogen-powered stars wouldn't exist. No steady light and heat from stars like our sun. Life would have no chance to evolve over billions of years. A dark universe without stellar engines. The strong force sits on a razor's edge. A little weaker, only hydrogen. A little stronger, no hydrogen fuel for stars. Our existence depends on this value being almost exact. It's not the only dial with unnerving precision. The universe we live in is a very special place indeed. Let's turn our attention to another crucial dial on the cosmic control panel, gravity. It feels strong to us, pinning us to our planet, but in the grand scheme of the universe's forces, gravity is astonishingly weak. It's trillions upon trillions of times weaker than the electromagnetic force that holds atoms together. But what if it were different? Let's imagine turning the gravity dial up, making it just a little bit stronger. Not much, just enough to notice. The consequences would ripple through the entire history and structure of the cosmos, erasing any chance for our existence. If gravity were stronger, stars would form from much smaller clouds of gas, and they would burn through their nuclear fuel at a furious, unsustainable rate. A star like our sun, which has a lifespan of about 10 billion years, might only last for a few million. This isn't nearly enough time for the slow, patient process of evolution to craft complex life on any orbiting planets. Furthermore, a stronger gravity would mean that galaxies would be more tightly packed and chaotic, leading to disruptive collisions that would eject planets from their stable orbits, sterilizing any worlds that might have had a fleeting chance at life. Now, let's consider the opposite. What if gravity were even weaker than it already is? If we turn the dial down, the primordial clouds of gas and dust that formed after the Big Bang would never have had enough gravitational pull to collapse. They would simply keep expanding, thinning out into a cold, dark, and featureless void. There would be no clumping of matter, no galaxies would light up the cosmic darkness, no stars would ignite to forge the elements of life, no planets would coalesce to provide a home. A weaker gravity means a universe without structure, a diffuse and eternally empty expanse. And it's not just the big forces, even the tiniest particles have their part to play. Consider the mass of the electron. If the electron were just a bit heavier or a bit lighter, the delicate balance of chemistry would be thrown into chaos. The way atoms bond to form molecules, the very foundation of biology, would be completely different, and likely not in a good way. The stability of DNA, the properties of water, the very structure of the elements on the periodic table. It's another dial, another knife's edge, another testament to the improbable conditions that allow us to be here. We've looked at just a few of the cosmic dials, but there are many more. Another critical one is the cosmological constant, a term representing the energy of empty space itself. This value drives the accelerating expansion of our universe. For decades, physicists expected this number to be huge, but observations revealed it to be shockingly small. It's so close to zero, it's like measuring a continent and being accurate to a hair's width. This precision is mind-boggling. If the cosmological constant were large and positive, its repulsive force would have been overwhelming. It would have ripped the universe apart before matter could clump. Space would have expanded so violently that gravity couldn't form stars or galaxies. The universe would be a vast, cold, empty void with particles flying apart. A lonely, dead cosmos. What if it were large and negative? Then there'd be an inward pull instead of an outward push. Anti-gravity plus gravity would halt expansion and pull everything back. The cosmos would collapse in a big crunch long before life could form. The cosmic clock would tick only briefly before implosion. No time for stars to live and die. No time for planets to cool. Put all these fine-tuned constants together: strength of gravity, strong force, mass of the electron, cosmological constant, and dozens more. And the odds of a universe like ours by chance are staggeringly small. It's like a cosmic casino, trillions of dice, rolling a perfect score on the very first try. The probability is effectively zero. This is the heart of the fine-tuning puzzle. We face an impossible stroke of luck. How do we explain this? Faced with this profound puzzle, scientists and philosophers have proposed several possible explanations. The first one we'll explore is perhaps the most straightforward and also the most debated. It's called the Anthropic Principle. In its simplest form, known as the weak anthropic principle, it states that the observed values of the physical constants are the way they are, because if they were different, we wouldn't be here to observe them. It's a selection effect. We find ourselves in a universe capable of supporting life for the simple reason that we couldn't possibly find ourselves in one that wasn't. Think of it this way. It's not surprising that you find yourself living on a planet with liquid water, a stable orbit, a protective atmosphere. You wouldn't be surprised by this because you couldn't live on Mercury, with its scorching temperatures, or Jupiter, a turbulent ball of gas. You exist on Earth because Earth is one of the rare places where your existence is possible. The weak anthropic principle applies this same logic to the entire universe. However, some find this answer deeply unsatisfying. It tells us why we don't observe a life-prohibiting universe, but it doesn't explain why a life-permitting universe exists in the first place. It feels a bit like surviving a firing squad of 100 expert marksmen and explaining it by saying, well, if they hadn't all missed, I wouldn't be here to be surprised. The explanation is true, but it misses the bigger question. Why did they all miss? This dissatisfaction led some to propose a strong anthropic principle, which takes a more radical and philosophical leap. The strong anthropic principle suggests that the universe must, in some way, have been compelled to have properties that would eventually allow life to arise within it. This version hints that the emergence of consciousness is not just an accident, but is somehow a fundamental feature of the cosmos, almost as if the universe was destined to be observed. This is a much more controversial idea, as it steps away from testable science and toward metaphysics. It suggests a purpose or a goal for the cosmos, an idea that makes many scientists uncomfortable, but continues to fascinate philosophers. If the anthropic principle feels like an unsatisfying tautology, there is another mind-bending idea that gives it real scientific teeth: the multiverse. This isn't just a comic book fantasy. The concept of a multiverse emerges from several of our most advanced physical theories, including string theory and eternal inflation. The idea is that our universe isn't the only one. Instead, it's just one bubble in a vast cosmic ocean of other universes, a multiverse. And in this cosmic foam, each bubble universe could have different laws of physics and different values for its fundamental constants. In this scenario, the vast majority of these universes are sterile and dead. One universe might collapse in a big crunch an instant after it's born. Another might expand so fast that no galaxies can form. Yet another might have a strong force so weak that only hydrogen can exist. These universes are born and die without ever producing anything complex, and there is no one inside them to witness their bland existence. But with an enormous, perhaps infinite number of universes, the improbable becomes inevitable. By sheer chance, a few universes, or maybe just one, will happen to have the dials set to the just right Goldilocks values that permit stars' planets life. Our universe, according to this theory, is simply one of those rare, lucky winners. We exist in this particular universe for the same reason we exist on Earth. It's one of the few places where we can. The multiverse theory thus provides a physical mechanism for the anthropic principle. The reason all the marksmen missed is that there were trillions of firing squads, and we are, by definition, the one survivor. This is a grand and spectacular vision. It solves the fine-tuning problem by replacing unbelievable luck with a statistical certainty across an immense cosmic landscape. However, there's a major catch. How could we ever test it? By definition, these other universes are causally disconnected from our own. We can't see them, touch them, or run experiments on them. For this reason, some critics argue that the multiverse is not a scientific theory at all, but rather a philosophical preference. It remains a tantalizing yet unproven explanation for our improbable existence. What if there's no lottery and no multiverse? What if our universe isn't lucky, but necessary? This is the third major avenue of thought, the possibility of a deeper, more fundamental theory. Perhaps the constants of nature that we see are not independent at all. Maybe there is a yet undiscovered theory of everything that will show us that these values are all mathematically linked. Such a theory would demonstrate that for the universe to be logically consistent, the strength of gravity, the mass of the electron, all the other constants had to have the values they do. Think of it like the number pi. The ratio of a circle's circumference to its diameter is not a random number. It has to be approximately 3.14159. It couldn't be 4 or 5 or 20. The very geometry of a circle demands it be pi. In the same way, a final theory might show that the constants of nature are as fixed and necessary as pi. In this view, there are no dials to turn. The cosmic control panel is a facade. The dials are all locked in place by a deeper mathematical logic. The universe is the way it is because it's the only way it could be. This is, in many ways, the dream of physicists like Albert Einstein, who spent the latter part of his life searching for a unified field theory. He couldn't accept the idea that God plays dice with the universe. The discovery of such a theory would be the ultimate triumph of science, revealing the hidden blueprint of the cosmos. It would explain away the fine-tuning problem as a misunderstanding. We perceive it as fine-tuned only because we don't yet see the underlying connections that determine everything. But this, too, leaves us with a profound mystery. If a final theory shows that the constants of nature must be what they are, and those values also happen to be perfect for life, what do we make of that? Does this incredible coincidence point towards something beyond science? Does it imply that the fundamental logic of the universe itself is somehow biased toward life and consciousness? Or is it the ultimate brute fact, a universe that is both mathematically necessary and, by sheer coincidence, hospitable? This question pushes us to the edge of what science can answer and invites us to wonder. The fine-tuning of our universe is a mystery that challenges our understanding of existence. What do you think explains it? Share your thoughts below. If you found this journey thought-provoking, hit that like button and subscribe for more deep dives into the cosmos.